It's a huge pleasure for me to introduce Professor Ben Sauer to you. Ben and I have worked together for the last 25 years, so I know him pretty well. He did his PhD at the State University of New York in Stony Brook with Peter Koch. He worked on microwave ionization of Rydberg atoms of hydrogen to study quantum chaos. And Peter Koch bumped into me at a conference and said, I've got this young guy who's a really brilliant experimenter. You really ought to hire him. So that's what happened. And at that time in 1992 at Yale. And then we knew at that time that experiments on atoms had shown that the electron had a remarkably small electric dipole moment, which is to say it was surprisingly round. But we also knew that you could do a lot better if you could figure out a way to do the experiment with molecules. So Ben's first job was to work out what would be a good molecule to do this experiment on. And I have to say, some of you may remember, this was before Google, so it was actually very hard to find anything out about anything. And so Ben went off for a few months and thought about what would be a good molecule to do such an experiment, and he came back to me and said, I found the molecule, it's a terbium fluoride. Now I have to say, this was hardly an obvious choice. It's a radical, it doesn't have any vapor pressure in the gas phase, it turns into other stuff. There was nothing known about its spectrum, it had only been seen in flames. So it was a bit daunting, and Ben actually outlined 1,000 reasons why this experiment would never work. And then he spent the next 10 years proving himself wrong. Actually, after all these years, a terbium fluoride still looks like the best choice that there is. And I should mention that in our group, Ben is famous for saying, oh, it'll never work, and then making it work. But so I'm getting a little bit ahead of myself. In 1996, we moved from Yale University to the UK, to Sussex, where Ben became an EPSRC Advanced Fellow and then a lecturer. And at Sussex, Ben got the first results on the electric dipole moment experiment, together with our brilliant student, Johnny Hudson, who's come to see this lecture. And in 2006, we moved from Sussex to Imperial. So we came here to form the Centre for Cold Matter. And there, together with Mike Tarbert, we started another possibly interminable project to see if we could learn how to laser cool and trap molecules. The motivation for that was, in the beginning, was to make the electric dipole moment experiment better. But that's now taken on a life of its own and is a major activity where I have to say Ben and Mike really lead the world in this area of laser cooling and trapping molecules. At Imperial, Ben became a reader and then a professor, which is, of course, why we're here. In the Centre for Cold Matter, Ben is the experimenter's experimenter. He is the linchpin of the lab. He knows where everything is. He knows how everything works. And he devotes his life to helping the students and making sure that results happen. And he has a very impressive record of wonderful results, some of which he's going to tell you about today, I hope, if there's any time left. So I'm really proud and delighted to introduce my friend and colleague, Professor Ben Sauer.
I should thank you all for coming out on such a warm evening. And also, I should thank you, those of you who read the emails that were sent around to Imperial today and have probably either redefined what your working hours are or redefined what it means to go home. Because this apparently is the day you're supposed to go home on time. And so I think we have some time still to do this. Okay, so I think we'll dive right in. So this was the introduction, of course. As Ed said, we not only have Google now, we also have Wikipedia. So I thought I'd introduce the thing by looking at starting with the Wikipedia, and you realize there's a Wikipedia page on unsolved problems in physics. And there are quite a lot of unsolved problems in physics. Some of them are more interesting problems than others. But if we look under the cosmology and general relativity, there's zillions of them up there, of course. And we're going to zoom in on just one of them. So what they say baryon asymmetry. And that's a question about why there's more matter than antimatter in the observable universe. And that's the main point about what I'm going to talk about this evening. So I'm going to try to explain what that problem actually is and how we go about addressing it. If you go ahead on Wikipedia and you click on that barium asymmetry list, you get this, which I don't think you can even read. I've actually cut off some of the text. But there are three main things. So there's the top one is CP violations, which if you read that, you still wouldn't understand what it was about. But I hope to explain at least what the words mean on CP violation. The middle one is regions of the universe where antimatter dominates. Actually, that doesn't happen. There are no regions of the universe where antimatter dominates. The universe that we see is made of matter. And the last one is the electric dipole moment. And it's very weird that maybe that the baryon asymmetry has these three sort of slightly seemingly unrelated things. So I hope to tell you about electric dipole moments towards by the time we get through this talk. Okay, but let's start first with the matter and antimatter. And there's a very, very famous physicist, Paul Dirac. For physicists, he's probably at least as famous as Einstein, but for the general population, most people probably haven't heard of him. And he did an absolutely amazing thing. He was in the 20s and early 1930s. He combined special relativity, so Einstein's theory of special relativity, with quantum mechanics. And I think he's famous because he did it in the most elegant way possible. He just thought, what is the simplest mathematical theory that could actually contain what was known about quantum mechanics and also has special relativity? And he wrote that down, and the theory actually had two consequences which were completely unexpected at the beginning. You know, he was just trying to get special relativity into quantum mechanics. The first was that he got very strange solutions from the mathematics that he realized actually corresponded not to electrons. It was really a theory of the quantum mechanics of electrons, but actually the theory of antimatter, so what are called positrons. And so probably most people have had a vague idea about what positrons are. They're absolutely identical to electrons, but opposite in a way. They have the opposite charge. And of course, famously, when an electron and a positron meet, they'll annihilate and give you a burst of pure energy, of pure light. And so that idea has been generalized. And of course, every particle that's known has its antiparticle. So the electron's the only one that got a special name, positron. The rest of them are just antiprotons, antineutrons, building up to anti-atoms if you really work very hard. So that's one thing that just fell out of Dirac's theory completely unexpectedly. Okay, and that gives us our first symmetry. So we talked about CP violation. That's the C. So the mathematical operation, you do the quantum mechanics and you write down what an electron is mathematically. There's a mathematical operation you can do called charge conjugation, and that turns the particles into antiparticles. And so C is just a mathematical operation. C symmetry is the question, is the physics same? Would physics be exactly the same if you converted all of the particles in your experiment into antiparticles? If you did a measurement, could you actually see any difference in that? And so that's one question you could ask. That's not a question we can actually ask experimentally, really. It's very difficult. It's only been in the last few years that people have even made anti-hydrogen. There's some other symmetries, which I'll very briefly explain. So the next one is actually mirror symmetry, so left-right symmetry. And physicists give this mathematical operation the name parity, so that's the P. And so what I've drawn here is a very schematic thing. So I have a sphere, and I can look at the mirror reflection of a sphere, and that's very boring. So there is no difference in a sphere in the mirror and a normal sphere. So you would say a sphere is a perfectly symmetric object under P symmetry. You can do a little bit more complicated sphere. So here's a sphere, a billiard ball that I've colored red on one end and blue on the other. I can reflect that in a mirror, and of course that flips the colors around. But of course, this by itself is not enough to show anything interesting, because I could take those two colored balls and I could rotate them around and show they're absolutely identical. What is interesting, I'm not going to go into it for this talk because we'll run out of time, but if you do a slightly more, if you look at just a slightly more complicated system, then you can come up with a system where when you look at its mirror reflection, it's not actually the same. And it's a very interesting thing that actually you can find nuclei in particular where their mirror image doesn't exist. So they're physical processes where the mirror image doesn't go, and very fundamental physical processes. And so that's called parity violation. And I'll say, I think, I was trying to remember when I first found out about parity violation. I think it was when I was an undergraduate. And I thought it was really kind of fascinating that this very fundamental thing, a very fundamental particle, could tell the difference between being left-handed and right-handed, because that's what a mirror inversion does. It converts left hands to right hands. And so I thought that was really amazing, and I'm still actually kind of amazed by it. I think this parity violation was discovered in the 1950s, and I think by now physicists kind of take it for granted. They know that in particular that weak interactions violate parity. They violate this left-right symmetry, and everybody just accepts that. But it's very, very strange. Why should a fundamental particle, nothing else around it, actually know to be left-handed or right-handed? It's odd. I was also fascinated to find out that you could do atomic physics experiments and actually measure these parity violating effects. I think that's quite amazing. I didn't quite go into that field, though. So physicists now kind of take that for granted. In the 50s, they certainly didn't. It bothered some very famous physicists. And they came up with the idea that, in fact, that this left-right symmetry violation is actually due to the presence of matter. And you weren't quite looking at the symmetry the right way. And actually, it's the combined symmetry of reflecting everything left to right and reflecting everything so that particles go to antiparticles and vice versa. That should be the good symmetry. And so that combination is called CP violation. And that's almost a good symmetry. There's an even more mysterious problem that even CP symmetry is not quite a good symmetry, but it's a much better symmetry than parity on its own. So then we come to the problem of the universe. When we look out in the universe, all we actually see is matter. And so the laws of physics are almost perfectly symmetric with matter and antimatter. And yet the observable universe is only matter. If there was antimatter, the first thing you always think is that there's some regions are matter and some regions are antimatter. But of course, when matter and antimatter interact, they annihilate each other, and you're just left with light or radiation. So they're very characteristic X-rays or gamma rays that are emitted when matter and antimatter annihilate. And we just don't see that in the universe. There's absolutely no evidence. So the universe is really made of matter. And that's a problem. The laws of physics don't allow that from the Big Bang. In fact, the universe is not even made of matter. I have to say, when you look at it, we don't really know very much about cosmology. Almost all of the universe is made up of dark energy and dark matter, which are just words to describe things that we observe that aren't explained by existing physics. So most of, if you run the Big Bang, you don't get anything with what we know about physics. We don't get the universe out at all. So that's a big problem. And if you look back at the Wikipedia page of the mysteries or unsolved problems in physics, quite a lot of them are to do with what's going on with how the universe gets to the Big Bang to where we are. But I'm not going to talk about that. I'm just trying to sort of motivate why on earth we're doing these experiments. So what we have, if you recall, so matter and antimatter annihilate and just give you light or energy or radiation. And so the paradox is, of course, the Big Bang, the universe started very, very hot. There was only radiation. The idea is that should condense out into matter and antimatter more or less equally, because that's what the laws of physics we know actually say should happen. And of course, if it condenses out to matter and antimatter equally, then all of that matter and antimatter will then find each other and annihilate because it's oppositely charged, and you'll get back with nothing left in the universe but radiation again. So it'll expand out, and you'll only have a very cool but universe with nothing much in it. And so that doesn't happen. And so something has to break that symmetry. And the thing that's needed is a violation of the CP symmetry. And so there's a fairly big industry in physics to actually look for violations of CP symmetry, to actually find out something that would actually give this effect and allow our cosmological models to actually work. You don't actually need very much. What you need is something like the rates to differ to going to matter to antimatter by about 1 in a billion, and then you'll, instead of just coming out with pure energy after the Big Bang, you'll end up with a little bit of matter left over and a lot of light anyway. There's a lot of microwave in the universe. There's one more symmetry we have to talk about, which I'll come back to later, and that's time reversal symmetry. And time reversal symmetry is exactly what you think it is. It just means you take a picture of some physical event, and you take a movie of it, and you play the video backwards. So again, if I go to my simple example, I just have a sphere. If I play the movie of a sphere sitting there backwards, you can't tell forwards or backwards at all. So you'd say that's a very time reversal symmetric situation. So what I can do is I can take a sphere and I can spin it. So this is supposed to represent a spinning sphere. And so the arrow, if you know the right-hand rule, is pointing to the right there. And if I play that movie backwards, it just rotates the other way. And so then the thing is pointing the other way, the angular momentum of the sphere. So that's a time reversal on a very simple system. Again, there's nothing wrong with this, because you couldn't tell that you were living in looking at a sphere. You couldn't tell you were here or in a time reverse version, because in both cases you just have a spinning sphere. There's nothing more interesting than that. So we'll come back to that and show how you can actually break this kind of symmetry. But that's time reversal. I thought I should stick a slide in and say what time reversal is not. And you're used to time reversal in everyday life, because you know if you drop your teapot on the floor and it shatters, then there's no way that you can take a bunch of shards of a teapot on the floor and have them jump back together and make a perfectly functional teapot. And that's a question of having a lot of particles around. And so I've got a little movie here which shows that. So what we've actually shown here is this J is made up of a bunch of little particles, and they're moving on a hilly landscape, so a potential landscape where the colors are different heights or different contours. And so they start out with some random velocities, and you know what happens. They bounce out and they bounce around for a while, and they end up in this very disordered state. And so that's time running forwards in normal mechanics. We can look at the opposite situation where we run time backwards. And so we start with a bunch of particles with a bunch of random motion, and they all come back together and form a big J. You know that never happens. And so that kind of time reversal violation is just the time reversal violation of having a large number of particles. And of course, this demonstrates something else as well. This shows that Newtonian mechanics, so the mechanics of balls rolling around on hills, is perfectly time reversal symmetric. Because what I've done in the second slide, of course, is just take all of the velocities and reverse them, which is equivalent to reversing the direction of time. And so Newtonian mechanics is perfectly time reversal symmetric. But that's not what we care about. The reason this never happens is you can never set up all of the particles with the right positions and velocities. So it's an initial value problem. Right, that's not what we want to do. That's what we want to do. So that's not the kind of time reversal we care about. What we care about is time reversal at the level of fundamental particles, not time reversal where you have an initial value problem, where your problem is just not being able to set up all the conditions correctly. Okay, and so then we'll come back to something which you more or less have to take on faith, is that when you look at these three symmetries I've talked about, charge conjugation, mirror symmetry, and time reversal, all three of those reflections together are required by special relativity. So Einstein's theory of special relativity requires that all of physics be symmetric when you apply all three of those reversals. And there's very good evidence for special relativity, of course. So C, P, and T together are a perfect symmetry. But we know that if we want to get matter out of the Big Bang, that CP must be violated. And so we conclude that time reversal is actually violated. So there should be right at the fundamental particle level, we should be able to find evidence of time reversal violation. And so that's the thing I've been looking for 20 years. Right, and so this is just a summary of where we have. So special relativity is really one of the best tested physical theories we have. It seems unlikely we'll find any holes in that. And so that tells you that CPT is almost certainly a good symmetry. That's just a mathematical proof. But at the same time, we're made out of matter, and we're not getting annihilated by a wall of antimatter coming through. So there seems to be some problem if you have a Big Bang to getting to where we are now. And so the rest of the talk, I'm really going to talk about the way we look for this new kind of time reversal symmetry. And so we're going to move on to the electron. And for those of you who are not physicists, I'm going to give a little introduction on electrons. So just some facts. All electrons are exactly the same, really perfectly identical. They have mass. And if you pick the right units, you can just write the mass as 1m, or 1m with a subscript e. They have charge, and again, if you pick the right units, they're negatively charged, so the charge is minus e. They're completely stable. The only way you'll ever get rid of an electron is to find a positron somewhere and annihilate it. And so we have a lot of electrons around. They have spin, which I'll come back to in a minute, and they have a magnetic moment. So the electron itself acts like a little magnet, and I'll come back to that as well. But what I haven't said here is anything about the size of the electron. So I haven't answered the question, how big is an electron? And that's kind of a problem. So one statement, which is really a mathematical statement, is you say an electron has no size. It's actually just a point particle. And so that's mathematically true, but actually kind of difficult kind of physically it's a little bit difficult. So we're going to talk a little bit more generally about size of electrons. And so electrons are very, very small. We know very, very small objects implies you ought to think about quantum mechanics. And so electrons have a wave function, or in the way people often talk about it, they're both a wave and a particle at the same time. And in particular, electrons describe, or they define, the size of atoms and molecules. And I'm more or less an atomic physicist, and so that's more what I care about when I think about electrons. So let's think about atoms a little bit. And so I'll start by showing a picture of something which is not an atom. So you might think, this is often when you talk about hydrogen, this is what people think about. They think of the proton, the big orange blob, and the electron, the little blue blob, and the electron orbits around the proton. That's not what atoms do. So this is more like an atom. You remember, the electron has a wave function. The wave function tells you the probability of finding the electron at any point. And so if you have a proton, then you just have some probability of finding the electron at some point around the proton. And at least for hydrogen and the lowest energy level and so on, that's perfectly spherically symmetric. And in fact, there's nothing orbiting there. The electron is just sort of held around the proton to make a hydrogen atom. When you say an electron is a point particle, what you mean is when you calculate the properties of a hydrogen atom, you look at the probability of finding the electron, and you go point by point and average over all of the possible locations, and that gives you the properties of the hydrogen atom. So you average over the whole wave function. So mathematically, you do treat it as a point particle, but physically, it's just sort of stuck on there. And for physicists in the audience, you can think about what is the size of a free electron. So you ought to think about mathematically how you usually describe free electrons. Anyway, so to give you a sense of scale, because we'll be doing some scaling, let's think about the size of an atom. So if we look at the ratio of a person to a bacteria, and then that's about the same ratio as the ratio of the size of a bacteria to the size of an atom. So that gives you some sense of scale. You don't notice that you're just full of bacteria. Bacteria clearly doesn't notice that it's full of atoms. So it's actually a long way down. So what we can say, another way to say the electron is a point particle is to say that the electron has no internal structure. And that's good. I'll use scientific notation here. It has no structure, something at the level of 10 to the minus 18 meters. If you don't know scientific notation, the minus 18 means that there's a decimal point, 17 zeros, and then the first number. So that's a lot of zeros. That's very small. I mean, if you look at it, that size is roughly the scale of a person to an atom. If you then blew the atom up to the size of a person, then the electron has no structure at the size of an atom compared to that. So it's like 2 jumps down from the person to electrons, or to person to atom scale. So in that sense, electron's a point particle. I thought I'd throw in a little bit of extra physics. And so that's to say that there might actually be a smallest length. We're used to the idea that you can't divide matter continuously. You can take this desk and start chopping it up. Eventually you chop it up small enough that you're down to the scale of atoms and then electrons and protons, and you can't get much smaller. It turns out space or length itself might actually have a smallest length as well. And that would be what's called the Planck length, which is about 10 to the minus 35 meters. So again, that's a decimal point, 34 zeros in front of it. And the idea is once you get that small, you can't actually have any space that's any smaller. So space is quantized, you would say. And so if you think about that in terms of scale, so person to an atom, blow up the atom to the size of a person, then person to the size of the atom, blow up the atom to the size of a person, and then sort of go halfway down again. So it's very, very far down. So the Planck length is incredibly tiny. Remember, the point at where we know the electron has no structure is sort of in the middle here in these ratios. And actually, if you want to know what's true, nobody has the foggiest idea about what's going on at the Planck length. That's very, very small. There's a lot of speculation. Anyway, so the summary of that bit is electrons have no size, but if they had any size, it would be really very, very small. Okay, going back to or spin. This is something where this sort of planetary model of the atom maybe has a little bit of value, at least to remind you what's going on. Because you know the sun spins on its axis and the Earth spins on its axis as well as orbiting around the sun. And so it turns out both protons and electrons have this internal angular momentum. So they spin on their axis as well. And so if the electron was like the Earth, it would definitely be spinning around. It's a little bit difficult to understand how a point particle can actually have angular momentum, but at the same time, it's actually a little bit difficult to understand how a point particle can even have mass like the electron, because that implies that it has infinite density. So there's obviously some mathematical problems with thinking about the electron as a point particle. Anyway, it's undeniably true that electrons have spin. And electrons are magnetic, so because they have angular momentum in their charge, they act like little magnets. And so this comes back to the second triumph of Dirac's theory, which he didn't certainly expect when he started writing it down, is that when he wrote down this theory, he got relativity and quantum mechanics, and he got antiparticles, but he also got this beautiful prediction that the ratio of the magnetic moment of the electron to the spin, so how big the magnet is relative to its spin, is 2 exactly when you put it in the right units. And that's absolutely beautiful just to come out with that prediction like that. And so that's really just a triumph of pure thinking. So that's a number that's actually been measured very, very carefully. And in fact, that ratio of magnetic moment to spin is not 2 exactly. It differs by about a part in 1,000. And in fact, it's one of the most precisely measured, actually I think it is the most precisely measured value in all of physics. So there are a lot of digits there. So a lot is known about this spin to magnetic moment ratio. And the question is where that's coming from. And that gets on to the reason we're doing our experiments. So that comes from quantum mechanics, but quantum mechanics not just of electrons, but thinking about other particles, in particular light, not as a field, but as individual photon particles. And so this diagram here, this is a Feynman diagram, this is actually a calculation. So this is a set of instructions to do a calculation to get a number out. And that number out is the first 2 after the decimal point, more or less. But the great thing about Feynman diagrams is you can also read them as cartoons and have a picture about what's going on. So what this cartoon says is that the solid line is an electron traveling along from left to right. And it goes along, and this wavy line is supposed to be a photon. So it emits a photon, and then as it goes along a little bit further, this is another photon that comes in. This one that comes in from the bottom is actually the electron interacting with the magnetic field that allows you to measure its magnetic moment. But then a little while later, it absorbs that first photon. And so that's kind of a quantum mechanical accounting trick. Anything can happen, but everything has to total up at the beginning, at the end. So you have an electron in and you have an electron out, but there's this extra photon that pops out from nowhere and then disappears again. That's kind of like if you're an academic and you have a grant. You get the grant award, you do anything you want during the grant, but at the end you better make sure that everything tallies up and you haven't spent too much or too little on the grant. So right, and so that's a calculation. And in fact, you can go ahead, it turns out lots of things can happen. So these are a whole set of Feynman diagrams that are actually used to calculate this. And so this is schematically a bunch of different calculations which contribute to this ratio of magnetic moment to spin. And you can see there are a lot of complicated things that happen. And so lots of things can pop out of the vacuum and then get other things pop out of the vacuum and so on. And there's a well-defined procedure for writing down all of these graphs, calculating them, summing up all of the contributions. But the important thing is that any particle that exists can actually pop out of the vacuum, contribute to one of these diagrams, and then disappear at the end. So of course the reason for doing these kind of measurements is it's a very indirect way of looking for new particles. And so the conclusion is the vacuum is not just a constant thing. The vacuum is very complicated. And that's why Dirac predicted 2 exactly, whereas as we now know, physics is not 2. Dirac didn't understand that or at the beginning didn't understand that the vacuum was so complicated. So anyway, just to summarize that, so this is again this ratio. So all of these leading digits are basically known particles. So they're mostly electrons and positrons and photons popping out of the vacuum. And so the point of these experiments, the reason this is measured so precisely, is actually trying to find new particles, and they're lurking down in the last digit, and so they're kind of obscured by uncertainties in the measurement and uncertainties in the calculation at the moment. Anyway, so that's all a very roundabout way of talking about something that I don't actually work on, but it's at least related to what I work on. So. Okay, so let's talk about electric dipoles, which is what I actually do work on. And so what an electric dipole means, we know the electron is negative. And so I'm going to think of the electron as a blob, a sphere of charge. But I'm going to allow it to be a little bit more positive on one end and a little bit more negative on the other. And I've also drawn it rotating. So I've drawn it spinning around its axis, and I've drawn an arrow for the direction of the rotation. So that's my electron. And so now we can go and look at our time reversal and an electron with an electric dipole moment. Again, I've drawn, if you look just at a sphere without anything else on it, you can't tell the difference between time running one way and time running the other way. And of course, when you look at a spinning sphere, the spin reverses, But again, you can't really tell the difference one or the other because I can just take this one and rotate it around and they look exactly the same. But if you have a dipole, it's a little bit different. So now, if I look at the dipole and I look at the time reverse of the dipole, of course the charge distribution doesn't change. So the positive end is still on the right. I said blue was positive, and the negative end is on the left. But the time reverse reverses a spin. So I can take these and just rotate them around and make the dipoles, the electric dipoles, point in the same direction. And then you see that you actually have two kinds of electrons. You have electrons with the blue ends up and the spin up, and you have electrons with the blue end up and the spin down. So that tells you, so that's what a dipole would do to an electron. And you come to the fundamental problem that the world does not contain two kinds of electrons. And so if there is a dipole moment, so if there is an electric dipole moment of the electron, then something is actually chosen to have either this kind of electron or that kind of electron. But they're definitely not both of those kinds of electrons. So that's what we mean by an electric dipole moment breaking time reversal symmetry. It would be perfectly fine if we knew there were two kinds of electrons in the world, but they're not. Okay, so let's take just one of these electrons and we'll put it in an electric field. And so what you know, so these green lines are supposed to be electric field lines. What you know about electric field lines is positive charges move in the direction of the arrow, negative charges move against the direction of the arrow. So if I've got these two electrons, then I look at the forces on the electron. We can see for the top electron, the positive end is pulled to the right and the negative to the left. So that's perfectly fine, it's just kind of stretched. On the other one, it's the left side is pulled to the right and the right is to the left. So that's an unstable situation. The electron would rather flip around and point the other way. But of course, it can't flip around unless something happens to it because it's got angular momentum. It's just like a bicycle wheel. It doesn't want to change its direction. So the lower in physics term, we say the lower electron has a higher energy than the upper electron. You'll instantly spot a problem with this because remember, electrons overall are negative charge. I've just added this electric dipole as a little bit of distortion of the electric charge. So what actually happens when you put those electrons in an electric field is the electric field just accelerates them out of your experiment and you don't have anything to measure one way or the other. So that doesn't work directly. And the solution is actually to use a neutral molecule. And so if you use a neutral molecule, then the molecule can hold the electron. And if you choose the right molecule, you might actually even be able to measure something about the electric dipole moment of the electron. And so the molecule that I've been working with is YBF. And so it seems like maybe a complicated molecule. It's actually a one-electron molecule. It's got a bunch of filled shells which don't contribute anything at all to anything. And so in the ground state, it's very, very similar to actually the hydrogen atom, where you have a single electron and a nucleus, in this case a molecular core. YB is down here at the bottom of the periodic table. And actually the reason we choose such an exotic molecule is it turns out that you need a molecule where relativistic effects are important in order to actually get anything to measure. And so YBF is a nice molecule because it's heavy. YB is heavy, so ytterbium is a heavy atom. There are a lot of relativistic effects. And so you pick something from the bottom of the periodic table for this kind of thing. It turns out to be quite nice to work with experimentally as well. Anyway, so that's what we did. That's what I did actually back when I was at Yale, was find YB. And so it turns out not a lot was known about YBF when we started all this series of experiments. And so what I did is I looked through the literature on the number of papers that have been published on YBF spectroscopy. And the breakdown, I'm not quite winning. So the number of papers is, there were only 2 when I started on this. And so for a while, I actually had the majority of YBF spectroscopy papers had me as an author. But actually, somehow our work has inspired people to look at some more details in it, and the other ones have pulled ahead lately. So, and they're exciting papers like this, you know, perturbed hyperfine doubling and the A doublet pi 1/2, blah, blah, blah. So, that's a paper we published back in the 90s. For those of you who are on the academic career, I can say publishing papers like this is not a very good way to get promoted quickly. But it is actually necessary if you want to actually do something new. Right. And so we'll go on, and actually I'll finish off just talking a little bit about how the experiment works, how we actually do this experiment. So this is a cartoon of the experiment. So we have a beam. It's all in a vacuum system. So we make YBF molecules. We orient their spins in a direction, and we use some lasers and radio frequency stuff. So they're going along, and they go through a pump laser and so on. The goldish yellow rectangles are supposed to represent the electrodes of a capacitor, so electric field plates. And we put a very large voltage across the molecular beam. And then when we come out, we sort of probe what happens to the molecules. So that's the idea. I'll get to what happens in a little bit more detail in a second. But I mean, the basic idea, if you remember back a few slides, we're getting the electron with the spin pointing one way in the electric field and the spin pointing the other way in the electric field. And we're trying to look for a difference between those two orientations. So that's what this pumping and probing stuff is. That's arranging and detecting the directions of those spins. It really exists in the lab, so here's a little bit of the apparatus, which is not nearly as clear as the cartoon. But you can sort of see the reason on the cartoon that the plates are gold is that they really are gold. So they're gold coated. They're actually quite special. And you can see this thing here is a high voltage cable that's bringing some of the high voltage onto the plates. In this picture, the YBF molecules will be coming up vertically between the plates. And so all of this stuff is put together in the lab and then stuck in the vacuum system and sometimes made to work. So like I said, the plates are very special. So they're gold to give a very nice electric field, and they're very smooth, and the spacing is very, very precise. And so this is a picture of the plates before we put them in. So these are actually glass with a thin layer of gold on them. The other thing you can see is we have a lot of trouble with magnetic fields, and the thing you see reflected here is actually a bit of the magnetic shielding of the experiment. So that sets a scale, sort of. These are about 1 meter long or so. Okay, so how do you actually do the measurement? So there's a problem. We're looking for a very small effect. And so if we pointed an electron in a molecule one way and then the next molecule we point it in the other way, between those two measurements, the magnetic field in the lab might change, or the electric field might change, or so on. And so we just play a quantum mechanical trick where we know that the electron can actually point both ways at once. So we make an electron wave function where the spin is pointing to the left and right simultaneously. And that's very nice because that means that one electron, we do the measurement on one electron in a molecule at a time. And that molecule experiences exactly the same interactions. And so remember, what we're looking for is we're looking for a difference in energy for the electron with its spin pointing one way and the spin pointing the other way in an electric field. And that comes out as a phase. And so I thought I'd have a demonstration which actually tells you what phase is, although I think the physicists in the audience may know what a phase is already. So all we need to do is figure out how we get out of this menu and get back to the VGA menu. Display controls. Do you have any way to get to the VGA? There we go. Laptop VGA. And right.
Yeah, this should be fun.
Yep. So here we go. So this is an electronic demonstration of phase because it was actually too hard to bring in lasers and all of that for the experiment. What we have is two waves. We've got a yellow wave and a blue wave. And phase just means where the peak aligns. And so at the moment, they're both actually aligned. I can do a little bit of twiddling on the thing, and you can see I can make the peaks anti-aligned. So that's a phase shift. And so you can't actually tell the difference just on a single wave what the phase is. And so I've got an audio demonstration of this. And so I've got a yellow trace on the oscilloscope. I've got a yellow cable, which I'll plug into this amplifier. And I'll turn, it's either too quiet or too loud. Maybe we'll go for too quiet. So that's yellow. So that just sounds, so if you can remember that pitch, some people can remember that pitch. So that's yellow. I'll plug in blue. So this is actually a green cable. So green cable is a blue trace. So that sounds quite similar. And I can prove we're looking at that, and I can change the phase of that guy. And you can hear there's a little blip as I tune the phase, but in fact, the phase stays exactly, the tone stays exactly the same once the phase settles down. So there would be no way, you can't distinguish that from the yellow guy. So that or that, they just sound the same. So what you can do is add them together. So let's go back to where they're in phase. And so let's do that a bit. So the red trace is actually the sum of those two guys. You can barely see the red trace there, but it's a little bit. But I think you'll probably be able to hear the red trace a little bit better. So there it's a little bit louder because I've summed the two things together. And of course, when I change the phase and I'm looking at the sum, of course what happens is that when they're in phase, it's loud. When they're out of phase, it's quiet. So what you have to do in order to actually measure the phase is you've got to somehow add the two things together at the end and see if they're loud or quiet. So we can go back to the annoying loud sound. So that's phase. Right, and so that's exactly what we do with the electrons, but we don't listen to the sound. Instead of loud and soft for being in phase and out of phase, they're light and dark for in phase and out of phase. So if we go back to the regular presentation, send to both. Right, so we have our electrons. They're pointing one way with the wave function, and they're pointing the other way with the wave function. We're going to add those wave functions together at the end, and we're going to see if they're light or dark. And so that's what we come out with in the experiment. So this is a plot of the signal we get out of the experiment as a function of the phase. And in this case, it's a phase we do by putting on our own magnetic field. So if you look at zero phase, the red curve is light. So we get a big signal at zero phase for the red curve and a small signal for the blue one. We have a way to see, rather than the speaker where you can't hear the canceling waves, we have a way to measure the canceling ones as well. And as I change the phase, of course, I tune from zero. I tune from being light to being dark to being light as I tune the phase around. So that's the trick. So using that trick, we can measure the phase between those two parts of the electron wave function. One of them pointing with the electric field, one of them pointing against the electric field. And that's actually the heart of the measurement. That's what we want to measure. And so when we actually want to do this measurement, what we do, so we have these phase fringes going light and dark. We actually just park ourselves on the side, and over again, we just run a burst of YBF molecules through, measure the phase, get a number. It's noisy, so they're scattered around, but they're all scattered around some average value. And so what you do is you bin them all up, and then so you get a distribution. And then you decide, let's switch the electric field and do the whole thing over again. So you switch the electric field, do the whole thing again, and you get a different distribution. And then the entire question is this distribution you get when the electric field is pointing one way the same as a distribution when it's pointing the other way? So that's the experiment. This is an incredibly tedious thing to do because you have to make a lot of measurements in order to measure this. So this part of the experiment is all completely automated, so we don't have to be in the lab actually doing that constantly. The interesting thing is actually to think about what could shift that distribution when you switch the electric field from one direction to the other. That's not actually the charge distribution of the electron, but some other effect. So that's something you actually have to think about. To give you a sense of scale, this is very sensitive to magnetic fields. So we were very good at detecting a magnet that was ramping on, our experiment is in the basement. We detected a magnet ramping on the second floor of the building without any trouble at all. The magnetic field, you may or may not know, when your heart beats, there's an electrical pulse which causes the heart muscle to contract. That electrical pulse of current causes a magnetic field, and that's not a very big magnetic field. That magnetic field is about the size in a shot that we're trying to measure. And so we measure much more quickly, so a person we wouldn't see, but if somebody's heart was beating like a hummingbird, we might be able to see that. So that's the kind of thing. We have a lot of magnetic shielding. Right, anyway, so that's the experiment. One way or the other, and you look for this phase, you look for this energy difference of the electron with its spin directed one way or the other, the electric field. So the question is what it means. And so we go back to this diagram of the Feynman diagram and say there are contributions to these Feynman diagrams which actually produce an electric dipole moment of the electron. So there are new particles that could possibly cause some distortion of the charge around the electron. And so what we're looking for are some new particles that pops out of the vacuum and disappears again, but leaves its effect as a measurable dipole moment. Or maybe we're looking for some other kind of time reversal violation. Maybe we're looking, you may have heard of supersymmetric particles. So supersymmetry is an absolutely beautiful theory of physics. It solves a lot of problems with the standard model. The problem is there's not one single shred of experimental evidence that it actually exists. But if it did exist, it would give the electron quite a large dipole moment, and so we should be able to see it. So that's actually what we're looking for. We're looking for new things popping out of the vacuum and actually leaving an effect in our experiment. And so I'm almost done. I want to summarize and show kind of a busy graph about what it means. This is actually only a one-dimensional graph, so there's a lot of stuff. So what's on the horizontal axis is actually the size of this charge separation in the electron from the positive to the negative in terms of the charge of the electron E and in centimeters, and it's scientific notation. So you remember the structure of the electron, you can think of it as the charge of the electron moved a little bit from its center of mass. So the structure of the electron was way down here, so that we're well beyond that. What these gray boxes show are experiments that have tried to measure this and have come up with zero. And so the Imperial one, 2011, is our YBF experiment. The problem with actually showing, this is a very old idea to do this kind of experiment, but once you show it works, other people tend to jump into it. And so there have been two subsequent experiments, ACME, which was at Harvard, and an experiment at Gila in Boulder in the States. And they've got sort of about an order of magnitude better limits in R. So everything to the left of this is actually ruled out by experiments. And these colored bars are just supposed to go some theories where some physicists have actually predicted if this theory was true, this would be the size of the electron-electric dipole moment. And so you can see some of them are ruled out. This is your most naive version of supersymmetry, which seems completely ruled out by these experiments. I will say we're running the experiment still, and we'll move down into this level very shortly. So we've actually got some life in the experiment still. You remember the Planck length I talked about then, and so that's down in centimeters, it's 10 to the minus 33. Nobody's there yet, but that's really unknown territory in terms of what physics is. I'll just say we've got some plans to not do this small advance, but do a big advance down below to this level, which will really cut out a lot of theories. And that involves the last little bit I want to say. And so I'll just summarize with this last slide. So this is a picture, the publicity picture for the talk here. And those of you who are really, really good at YBF spectroscopy will realize that this is not the electron electric dipole moment experiment. These lasers are the wrong color to do YBF. So this is actually one of the other experiments I work on laser cooling calcium fluoride. And so I got into this laser cooling again because if we can cool molecules down, we can hold them for longer and make much better measurements. And so we're working on calcium fluoride because it's easier and there are lots of other things you can do with cold molecules. But we're also working on YBF laser cooling. And we have some nice preliminary results on using lasers to cool YBF as well. So we can see a way using these cooling techniques to make a big leap. And probably, well, you would hope that there's actually new physics out there solving this problem of the matter-antimatter balance in the universe. And there might actually be something there. But even if there's nothing there, we rule out an awful lot of theories and really cause trouble for the theory community. Okay, I think I should wrap up because it's hot and I've been going on a while. So I just want to thank everybody I've worked with so far. And in particular, of course, Ed Hines, Mike Turbot, and Johnny Hudson, who've been my colleagues for a long time now. And then there's been a whole series of people working on the EDM experiment, the laser cooling of calcium fluoride, and the laser cooling of YBF. And then finally, I'd also certainly like to thank the technical staff who work with us that make the experiments possible. And I'll finish there. There's some pictures there of various people in the group. There's no way I could find pictures of everybody who's ever worked on that. Well, that's sort of a subsample. Those in the know will recognize the middle group as most of the EDM people. All right, so I will finish there for now. Thanks. Yeah, that's fine.
Yeah, is that all right?
Yeah. Yeah.
So I'm Ivan Hughes. I'm a research colleague of Ben. I work at Durham University, and it's my pleasure this afternoon to give these few summary notes right at the end. So Ben and I have worked in the same research field for roughly a quarter of a century. We were both postdocs, trained under the expert mentorship of Ed many years ago. For people who aren't experts, I think one point I'd like to make about this field, there's a very wide range of experiments in atomic physics, from the, frankly, here today, gone tomorrow fads to the very important, very fundamental work. And Ben's career has been definitely the latter end of that spectrum. There's a misconception from the public that if you're doing something with fundamental physics, you need an experiment the size of a small country. Maybe you need to be in CERN. The Radio 4 Today program might have to be live from your lab. To the best of my knowledge, John Humphreys hasn't been in your lab yet, Ben, is that right? But I think one thing that was very clear from this afternoon's lecture was the fact that these experiments can, in fact, make very fundamental tests of physics beyond the standard model with the exquisite precision of atomic and molecular physics. So despite being knowledgeable about this field, I've also learned something this evening. I think I've just learnt that it is actually possible to listen to Ben speak for roughly an hour without having a pinout diagram of an obscure op-amp mentioned, because if you ever need a pinout diagram of an obscure op-amp, Ben is your man. And the guidelines as to the kind of things I should be mentioning, there was how did I meet the speaker? I met Ben at 3 a.m. at the bus station in New Haven, Connecticut. That's the low point in our career, I think. Things have got much better since then. I bring you greetings from the north, from Durham. Many people in the community in the UK can't come here today, Ben, but everyone sends their congratulations and best wishes. Quite a few of my colleagues, when they heard that I had the chance of saying a few words, wanted to share some anecdotes about the good old days. They're mostly formulaic. They essentially go along the lines of, do you remember when we went to that APS meeting in New York for one weekend and we woke up on a Tuesday in a dumpster in Connecticut? But Ben's mother is here, so I've decided I won't share all of these anecdotes. But if you are around for the drinks later, I am available to tell you what things were like in the good old days. I'd like to point out I started my physics career in this department. I spent a long time in this lecture theatre, sat over there, in fact. And I find it very heartening to see that the department still backs fundamental experiments where the timescale of impact, however you define that, is in decades rather than the typical period of a grant for 3 or 4 years. I was also very pleased to see that in the last but one slide, at least 3 of the PhD students that have worked with Ben, I taught at Durham. So you owe me, Ben, for that. I don't think it's a coincidence that I've steered quite a few people in this direction. I've been using Ben's research papers in my teaching for the last 20 years, essentially because of their elegance and significance. I'm also glad that this is actually the picture that we're currently projecting. Again, if you're not an expert, this is Ben in his natural environment, laboratory full of highly dangerous equipment. If you're not familiar with the taxonomy of risk, class 4 is the most dangerous. The exact wording for class 4 is you need to avoid direct or indirect exposure. I'm not talking about lasers at the minute, I'm talking about Ben's jacket. It's absolutely one thing that has not changed in the quarter of a century I've known Ben, is his definition of sartorial elegance. So I was trained here. I've also worked at another 5 universities. I've been very fortunate in my career to work with a huge number of very talented scientists. But to echo what Ed said earlier, without a hesitation, I can say, hands down, the most gifted experimental physicist I've ever had the pleasure to work with is Ben. Thank you for a wonderful talk. Congratulations on being promoted and best wishes for the future.
Well, it just remains for me to thank you all for coming, to apologize for the late start, which has caused us to have a correspondingly late finish. But now, if you go out the back, you can get wine and canapes. So enjoy yourselves, and thank you for coming.